as far as my experience is concerned, I divided this entire thing into keywords: encapsulation and then obviously abstraction. Whereas I am for abstraction, but the way people teach is encapsulated, it's hidden. And when I say abstraction, it means this. This is how you should understand or look at Pythagoras. This is the visual understanding. You know, the way you can learn from an image is exceedingly more clear than learning something just by repeating it. So abstraction means that you know the crux of it and you know the way how it really works. Let me come back on abstraction and encapsulation actually. The way our teaching system or our educational courses are devised, they are really a certain skill set that you have to learn how to do a Laplace transform and how to solve differential equations but right these days you don't really need to solve them. You have MATLAB to do these kind of things numerically to a certain accuracy which you desire, which you so desire. So in my opinion, and it might be wrong to say that it might not be really in line of what you might believe on this, but I think the age of teaching the first principles of equation is possibly out. We really don't need to know first principles until unless we know that how where exactly this entire thing has to be used. But this is a kind of controversial statement, so this is just my opinion. It should not be taken as a declaration, but this is just a kind of opinion on that particular point. So this encapsulation, idea of encapsulated teaching, it means that we should not really venture into a field until unless we know how this particular thing operates. So let me come to this particular thing on the abstraction part. You know this particular thing, which is the gravitational wave. Sometime back there was a lot of things which are news with regards to this LIGO. You all have actually went through this news and then their declaration that they have found a gravitational wave and all those kind of things. So did you try understanding what exactly is this? And how they just used some very, very simple principles and they found out how they proved that Einstein was right, which Einstein actually did with his abstraction 50 years back. So this thing is something which requires an abstraction of things like how, what exactly is the gravitational wave and how it travels, and whether a gravitational wave is just like a radio wave or is something else or whatever. So this is something where people like you should be inquisitive of how it works, how it has been caught. So I would not go to the detail of this thing, but I'll just share that this entire LIGO, the lab, has at each end they have reflectors, and there's a source laser, and then you just throw a laser, it reflects through within the tunnel and then travel a path of around 8 or 10 kilometers or something like that. And what they do is they actually try to find out the distance, change of distance by very, very precisely recording how much time it takes from hitting here and then coming back. So this is a very simple arrangement, but this is not that simple. You have a lot of interferences in between. So you have 3 LIGO reactors at different parts of the world. All of them simultaneously recorded a disturbance, and that's why they said it's the gravitational wave. Otherwise, earthquake might have actually created something like this. So it requires a certain abstraction of things like different places and understanding that earthquake would not be there on all places of same magnitude at the same time, something like that. So this is how you can understand, how you can abstractly understand how Pythagoras theorem works. Now this is very interesting. It is actually a metabolic rate of any living being plotted with the body mass of that particular living being. And you'll see that all of them lie together on a line. and the human being is somewhere here, and then you can see a rat is here, an elephant is here. So there's something else which is going on. So this kind of understanding can be developed graphically better than through equations. So I mean, okay, so maybe I have said in a different context, but how to unfold these kind of phenomena which are out there with us, how to unfold them. So it requires a certain level of abstraction, it requires a certain level of understanding that what can be related to what, and it requires an abstraction of things which requires understanding of the impact of various variables on a particular system. So an example of it can be like, it says, this particular graph says that as soon as you grow big, your metabolic rate grows further big. And the same thing is actually true for our urban spaces also, urban cities also. And why? Because a lot of research is going on this particular front. What they are doing is they are trying to actually correlate, and they are saying that I'm a complete, like I'm an organism which has a lot of network within it, and similarly our cities work in the same way, companies work in the same way, and the bigger is the company, the lesser is going to be the resources. So they are actually deducing the knowledge from here. So they are actually saying, the scientists are saying that Delhi is a big whale, or England is a big whale who is a large organism, and so they can actually deduce with this particular relation of 15% that if you have this, you are this big, then you must have per square kilometer this many petrol pumps. So this is something which is being deduced based on these things. So now a quick test for the students actually. Which one of these three for each slide is most comprehensible for you? I mean, the comprehensible. The one is this one. Okay. The second is this one, and the third is this one. Which one is most comprehensible for you? Which one you understood after looking at it?
First one.
First one. That's the problem.
Newton's method.
So, I mean, I'm not trying to undermine your thing, but the point that I'm trying to make is that instead of looking at equations, just as written equations, you need to really look at these things. This is the abstract understanding of how Newton-Raphson works. This is how Newton-Raphson works. And from this, you can actually say that the derivative and this component, fxn or fx dash n, as soon as it becomes minimal, you reach your solution. And here you are proving it. So my request would be that start looking at things in a different frame of mind, not in this frame of mind. This would only tell you this is Newton-Raphson method. But the way you look at this, it would tell you Newton-Raphson actually works on a derivative, and it keeps on calculating tangents, and as soon as your slope becomes something, and that whatever, then this is how it works. So for your lifetime, you will not lose the understanding of Newton-Raphson method. So this is something that is very important as far as the abstraction of things are concerned. So obviously, then you go to somebody who hires you, or a company came here and they ask you, what the real world skill you have? And then you say that I can give tests, which is the least required real world skill that you should be having. So why maths? And in fact, what is the real use of simulation?